Example 5. In 2003, Science magazine reported on a new computer-based test for ovarian cancer, clinical proteomics, that examines a blood sample for the presence of certain patterns of proteins. Ovarian cancer, though dangerous, is very rare, afflicting only 1 of every 5,000 women. The test is highly effective, able to correctly detect the presence of ovarian cancer in 99.97% of women who have the disease. However, it's unlikely to be used as a screening test in the general populations because the test gave false positives 5% of the time. Why are false positives such a big problem? Draw a tree diagram and determine the probability that a woman who tests positive using this method actually has ovarian cancer. So in this case, we know the probability that given they have cancer, they get a positive test. We want to work backwards and find that given they had a positive test, they actually had cancer. A tree diagram will help us find these probabilities. So now we're going to find the probability of A, which is has cancer, no cancer. First branch, 0.0002, which is the probability they have cancer. On the bottom, we have 0.9998, which is the probability of no cancer. In the next column, we have the probability of B given A, so given they have cancer, positive test, given they have cancer, negative test. We start with probability of given they have cancer, they have positive test, 0.9997. Probability that given they have cancer, they have a negative test is 0.0003. On the bottom, we have given they have cancer, what's the probability they have a positive test or a negative? So positive test given no cancer is 0.05, negative test given no cancer, 0.95. Now we do the probability of B and A, which is has cancer and positive test, 0.000199. Probability of has cancer and a negative test, 0.00000006. Probability of no cancer and a positive test, 0.04999. Probability of no cancer and a negative test is 0.94981. Now we're ready to calculate this to figure out our solutions, to find the probability of given a positive test, someone has cancer. So this will equal the probability of cancer and a positive test over the probability that they have a positive test. We'll have to add some stuff together to figure that. Probability of a positive test in cancer equals 0.000199 over 0.050189. So we had to add the two positive tests, has cancer, positive test, no cancer, positive test. We had to add those probabilities together. And this will equal 0.00397. So, the probability that someone with a positive test actually has cancer is only 0.00397. So this really means we'd expect about 4 people out of every 1,000 positive tests to have ovarian cancer. This test isn't really that accurate as a result, and so we're not going to use it.